So, we shall now start our discussion on global routing. So, you recall in our earlier lectures we have looked at the maze or area routing, where two arbitrary points on a two-dimensional surface could be connected, but one point was there, you recall, the entire path was laid out on a single layer. That was one of the restriction or requirement, whatever you say. But here in global routing and also subsequently detailed routing that you consist of, that kind of restriction is not there. We are allowed to use multiple layers for interconnections. Okay. So, global routing and detailed routing, they are not independent, they go hand in hand. Now, in contrast, the grid routing algorithms which we discussed, they are used not directly associated with global or detailed routing, but whenever we run into some problem we use area routing, because area routing is considered to be one where we can find path between 2 points which are otherwise not so easy to connect. So, if there is a path existing, it will find a path, but in these method detail or area routing, we are basically concentrating on small parts of our design or the layout, and we are trying to solve the routing problem in an incremental fashion. Okay. So, let us see the basic objectives of these two. Global routing is a step where you define something called routing regions. So, we shall be looking at this, and we generate a tentative route for each net. We do not tell you the exact route to follow. Like for example, if you want to go from a city A to city B, I can give you a tentative route saying that, well, you first go to town D, then go to town X, from where you can go to city B. But I do not tell you exactly which road or roads to follow to go to your other two towns, intermediate towns. There can be multiple ways to go there, but I give you a tentative route. This is my global routing. I only specify the tentative route, I do not lay out the exact wires at this stage. Okay. So, each interconnection net is assigned to a set of routing regions in this step. As I said, it does not specify the actual wire layouts. So, whereas in detailed routing, we actually complete the interconnections. So we considered this problem on a region by region basis typically, and we solve each of the regions by completing all wire layouts, vertical and horizontal, and this is what is done in detailed routing. So, here we shall see later there are two kinds of detailed routing sub problems, channel routing and switch box routing. So, we shall see this later. This is just an example. So, here you see some blocks, and these dotted lines show you the nets, the points which need to be connected. So, in global routing, here only some rough paths are shown. Like for example, when you connect let us say a point here to a point here, it says that you have to follow roughly this path, and alternative could have been you follow this path, or it could have said you can follow this path. Okay. So, global routing does this. One global routing process is done. So, each of these rough connections are actually mapped to horizontal and vertical segments. Now, again I repeat, here the solution that is shown is a 2-layer routing solution, where the horizontal lines are laid out on one layer, vertical lines are laid out on another layer, and any crossing here, this corresponds to something called a via connection, which means this is a connection between the two metal layers. Now, this detailed routing problem can be identified as routing or interconnecting points between two parallel surface, this is called a channel, or you consider a problem like this where you have an enclosed region where pins on all 4 sides, this is called a switch box. This can be a switch box routing. Okay. Now, let us come to the concept of routing regions. Routing regions are those through which interconnecting wires are laid out. Now, the question is how to define these regions. Like let me take an example. Let us say I have a rectangular layout surface where I have placed some blocks like this, one block here, one block here, one block here, let us say one block here and one block here. Now here once I placed it, so I can define some regions for routing. So, roughly I am showing this is one region, this is one region, this is one region, this is one region, this is one, and this is one. Now, in addition you can use this as regions also, because you can also make connections through this side. Okay. These are all routing regions. Now, you look at, let us say, places like this, where you have connections coming from 3 different sides. Some wires may come from top, some from bottom, some from this side, and also some from pins here. So, this can be a switch box kind of a problem, where pins are coming from all 4 sides. But a problem like this, where you have a parallel layers where some pins here and some pins here need to be connected, this is a channel. This is a horizontal channel, this is a vertical channel. Okay. So, the types of routing regions can be either a horizontal channel, which is parallel to the x axis with the pins corresponding to the nets at their top and bottom boundaries. Vertical channel is a 90-degree rotated version of that, which is parallel to the y axis, pins on the left and right. And switch box, as I said, it is a rectangular region with pins coming from all 4 sides. This is the more complex sub problem among the 3. See, horizontal and vertical channel routing problem are the same, it is just a 90-degree rotation, nothing else. Okay. So, the point to note is that during the global routing phase, the first important step is to identify the routing regions. So, we shall see that how routing regions can be typically identified later on, and routing regions for most of the design styles do not have prefixed capacities. Like sometimes you can move the blocks around, like in a standard cell you have the cells arranged in rows, but if you find that the space you have kept for the channel is not sufficient, you can always move the 2 blocks away a little bit, make space for the channel. Or if you see that that means you do not require that much space, you can bring them closer together. So, the width of the channels can be adjusted as per this situation. And also there is another point which we shall see a little later. The order in which the routing regions are considered is also important, because the overall routing quality and also the complexity depends on the order in which the routing regions are being considered. Okay. Talking about the channel junctions, so 3 types of channel junctions occur in layouts. First is called L type. You see, this is a block which is placed, there is a channel here vertical orientation, there is a channel here horizontal orientation, the 2 channels are connected as a L. Okay. This looks like an L, this is a L type channel. This typically occurs at the corners of the layout surface. So, here the ordering is not important, you can either route the vertical one first and then horizontal, or the reverse, and simple channel routing algorithms can be used for this. Well, we shall see these algorithms later. T type means this, a wide block and 2 smaller width blocks below it. So, you see there is a channel here, there is a channel here, 2 horizontal channels and 1 vertical channel here. So, the 3 channels form a T. Now, the idea is that you see here the concept is that the leg of the channel, that means this vertical channel has to be routed first. Let us try to understand why. This is an obstacle, let us say this is an obstacle, these are some cells and these are some pins which you want to connect. Let us say some pins are here, some pins are here and some pins are also here. So, what we say is that first we interconnect this leg of the T. Let us say we connect these points. So, these points can be extended here because they may also get connected to the other points, maybe this pin is also getting connected here, this is also connected here, fine. Now, the reason why this channel has to be connected first is that once you complete this, the position of these 3 signals are fixed. So, now this whole channel looks like a consistent channel routing problem, fixed pin location on the top, fixed pin location on the bottom. But if you do not consider this first, if you have considered this one initially, so in the middle you really do not know the exact position of these signals, it can be here, it can be here, it can be here. That is why once you do this, then you can route the other points like this, you can route this, you can route this, like this you can complete the routing. This you can possibly connect to this. So, for a T junction, the leg of the T has to be routed first and then the shoulder. But for a plus type, like here when there are 4 blocks like this, you see the central point here, there are pins coming from all 4 sides. This is a switch box routing problem and you just use switch box routers. So, you see during placement also it is advisable to place the blocks in this way, so that switch box problems does not appear, because channel routing problems are much simpler to solve as compared to the switch box routing problem. So, if you can change or modify your placement a little bit in such a way that such switch box kind of regions do not appear, then your routing problem can become simpler. Okay. There are some design style specific issues also, like for example, in the full custom design style, the problem formulation is exactly same as what we have discussed just now. So, all the types of routing regions like channel and switch boxes and the channel junctions L type, T type and plus type, they can occur. And I mentioned the channels can be expanded, some blocks can be moved here and there. So, some violation in the channel capacity can be allowed, but major violations are not allowed, because if you say that I have to move a block too much, then other blocks might get disturbed, right. So, some placement may need to be changed significantly in that case. Okay. Standard cell. So, in a standard cell, if you recall, the cells are placed along rows. So, after you complete the placement, the location of each cell is fixed, the capacity and location of each feed through is fixed. So, you recall I mentioned what is a feed through. Feed through are some special standard cells which allow a connection from top to go to the bottom, so that across rows you can take a connection and you can connect. Those are the feed through cells. So, what it says is that, so after placement you have already placed the feed through cells. and feed through cells have some predetermined capacity, how many such wires can be run across cells. But if you see that your routing problem is such that you cannot complete the routing using that many feed throughs, that means you are in a problem. You have to again go back, change the feed throughs and again come back to the routing. And for standard cell there are no vertical channels, only horizontal channels, and again you can move the rows so that heights can be adjusted. So, as I had mentioned, if feed throughs are not sufficient, routing might fail, and over the cell routing is a method which we shall be discussing later, which can be used to further reduce the channel height. Like an example I am shown here, like say these are 3 standard cell rows I am showing, and some interconnections have already been done across rows. So, there was one feed through cell here, one feed through cell, only 2. But suppose additionally you also have to interconnect A and B, you do not have any other feed through cell available. So, this routing will fail. So, what it means is that means either your placement is not good, this block should have been placed here, or means one more feed through cell should have been included here, so that you can complete this routing. Okay. This is one problem. And even for gate arrays where the location of the gates are fixed and also the number of interconnection lines that are allowed between them is fixed. So, routing channels and capacities are fixed. So, routability, like for example, if between the cells there is path only to run 2 parallel interconnection tracks, and so already you have made connections like this and like this. So, the red connection that is shown, this will fail, you cannot complete this, because this will need a third track, right. So, again for gate array your placement should be good enough, so that your routing can be completed. So, in global routing we use some graph theory based models, so which can be used to model the problem and also identify the regions. So, some of the important graph models are shown here, we shall be looking at them. The grid graph model is more suitable for grid routing, but we shall anyway talk about it here. This is more suitable for area or grid routing. Checkerboard model is also similar, but channel intersection graph is something which is the most suitable for global routing and is most widely used. Let us see these data structures one by one. Grid graph model, this actually models the same 2-dimensional grid pattern that were discussed earlier for maze routing algorithm, like for example, Lee's algorithm. So, we had a set of cells m by n, each cell contains some information and they were represented by either an obstacle or something. So, in general in the grid graph model, the layout is considered as a collection of square cells or grid. So, we define a graph where each cell C I represents a vertex V I and 2 vertices are connected by an edge if the corresponding cells are adjacent, right. Now, a terminal in cell C I, suppose I want to connect a point from C I, the terminal is assigned to the corresponding vertex V I. There are 2 kinds of vertices, some cells are occupied, which are represented as filled circles, but the unoccupied cells can be represented as clear circle. I shall show an example. So, in this model the capacity and the length of each edge is assumed to be 1. So, for every 2 terminal net, the task is to find a path between the corresponding vertices. Like let us take an example like this. So, I have a 2-dimensional grid like this, where the shaded regions represent the obstacles. So, I can map it to a graph where every region corresponds to a vertex, the adjacent regions are connected by an edge, the obstacles are denoted by solid vertices. Now, suppose I want to make a connection from this cell to this cell, this cell to this cell, which in this graph represents this vertex and this vertex. So, now the graph theoretic subproblem is find a path through this graph, not going through the solid vertices, find a path which can take you from here to here. So, once you get a path like this, you have found out a path. So, any area routing algorithm like Lee's algorithm or Hadlock's algorithm can be used to solve this. Okay. Now, checkerboard model is more area efficient. It approximates the layout not as a uniform array of fixed size cells or grids, but as a coarse grid. Some grid can be bigger, some grid can be smaller. Also, the edge capacities between two blocks are different. Like for example, there are two blocks, there can be one block like this. So, two scenarios I am showing. These are two blocks, this is one scenario. The other scenario is let us say this is a block B1 and B2 and this is a block B1, B2 and B3. So, for this problem, let us say I have a vertex for B1, I have a vertex for B2, they are adjacent. So, they are connected together and you see their boundary is totally unblocked, you can use the entire boundary for connection. So, I give a weight of 2, but in this case B1, B2 and B3. So, between B1 and B2 you see only half of it is available, the other half is shared with B3. So, I give a weight of 1, similarly between B1 and B3 I give a weight of 1, but between B2 and B3 the entire boundary is available. So, I give a weight of 2. So, weights can be assigned accordingly depending on whether the whole boundary between the blocks are available for routing or it is only partially available, right. So, this is what the checkerboard model is. So, here I am showing an example. There are 5 blocks placed in a rectangular region. So, how many regions are there? 1, 2, 3, 4, 5, 6, 7 and 8. So, there are 8 vertices. So, all the vertices are partially blocked. So, they are shown as solid. Now, these weights between these two regions, you see that the whole boundary is available for interconnection. So, weight is 2. Between these two regions, this block is partially blocking the boundary, that is why weight is 1. Similarly, between these two weight is 1, these two weight is 1, like that. Similarly, between these two regions the whole boundary is available, that is 2, others are all weight 1. So, you can see that the checkerboard model is more efficient in terms of space, the number of vertices in this graph will be much smaller, okay, and this is much easier to handle as compared to the grid graph model. Fine. Now, let us come to the representation which is most widely used for, you can say, global routing, particularly in connection with the standard cell routing problem, which is most widely used. So, just to recall, in a standard cell routing problem we have here, let me give two different scenarios. So, one is a standard cell routing problem where you have the cells arranged in rows, and you have identified channels between the rows, and also side by side we also consider full custom design style where also you can use this. Like here I have the blocks placed like this, let us take some examples like this. So, here also there are interconnection channels which are placed between the blocks. So, you can just identifying the interconnection regions or channels. Like here for example, I can have a channel here, I can have a channel here, I can have a channel here, a channel here, a channel here. In fact, this whole thing can be considered a single channel, this whole can be considered a single channel, and so on. Similarly, these can be regarded as channels. These are all channels. Okay. Similarly, this side, these are all channels. So, there are so many channels. You see, there are channels and some of the channels are intersecting, like for example, this channel and this channel are intersecting here, this channel and this channel are intersecting, this channel and this channel is intersecting, this channel and this channel is also intersecting. So, with this channel there is an intersection with 1, 2, 3, 4 more channels. The channel intersection graph basically models this kind of intersection between the channels, right. So, here each vertex represents a channel intersection. Now, the edges represent channels, right, and two vertices are connected by an edge if they are there is a channel intersection between them. Now, edge weight represents the capacity of the channel. Let us take an example. Suppose I have a just example like this, we ignore this embedded graph which is again shown here. There are 5 blocks placed in a rectangular region. So, as I showed in that example earlier, these are all examples of channels, these are all channel, this is a channel, this is a channel, and so on. And these red dots indicate the intersection between the channels, right. In the channel intersection graph, I only extract that information. The channel information is extracted as vertices, and the two channel intersection between which there is a common channel, that is connected by an edge. Now, it depends on the width of the channel, how many wires it can handle, you can assign some weights to the different edges, right. Now, see, the channel intersection graph directly keeps track of the channels and intersections, which is important for global routing, because in global routing what we are trying to do? We are trying to find out an approximate path between 2 points that are required to be connected. For example, I need to connect a point here on this channel to a point here, then means I can identify the nearest vertex. So, here also I can find out the nearest vertex. So, my problem is to find a path between these two vertices. This means I can find out which sequence of channels I need to follow to complete this routing, right. Now, a slight extension makes it more meaningful. Now, in this extended channel intersection graph, we use not only the channel intersections as vertices, but also the pins as vertices. Now, the rest remains same. So, let us see that how it looks like here. The same example I am showing here. In addition, I am showing some pins just for illustration, one here, one here, one here, and one here. What I am saying is that whenever there is a pin, there will be a vertex added in the corresponding channel edge. Okay. So, now if I want to connect a pin this to a pin this, I do not have to find out the nearest node, but I have a node or vertex corresponding to this pin directly. So, I have to find a path between this and this. So, there can be many paths, I can follow this path for example, right. So, going back. So, the global routing problem is basically to find a path in the channel intersection graph. The capacities of the edges must not be violated. For 2 terminal nets we consider sequentially, for multi terminal nets we can have approximation to minimum steiner tree. Okay. Let me take an example to illustrate how these regions are generated. A very simple example I take. Fine. So, let us name the channels. Let us call this channel as C1. Let us keep them separate. C2, let us call it C3, let us call it C4, let us call it C5, C6, C7, C8, C9, C10, C11 and C12. Let us now also consider some example nets, like for example, a pin here, let us call it 1, this has to be connected to a pin here, let us call it 1. Let us a pin here 2, this has to be connected to a pin here, this is 2. Let us take another one, a pin here 3, this has to be connected to a, let us say, pin here 3. So, there will be many such nets. Let us say, okay, yes, these are all 2 terminal nets, let us say. So, there is net number 1, net number 2, net number 3. So, what does this global routing problem or algorithm generates as output? So, I have shown the channel intersection graph model, you can get this information from there, represent it as a graph and find some path through that graph. Now, let us say, suppose I want to connect point 1 to point 1. So, for net 1, so you identify a path, let us say the path I follow will be this, which means I will be following the channels C1, C3, okay, there is another channel I missed, let us call it C13. C13. For N2, 2 and 2, let us say we will be following this path in a different color, let us show. So, N2 will be following first C3, then C13, then C9, then C8. Then N3, well N3, let us say I am following this path. So, net 3 will start with C6, then C1, then C2. So, for each of the nets I generate a sequence of the channels or the approximate paths that are to be followed. Now, from this what I get a complete specification, routing specification I mean, for let us say channel C1. Now, in this example 2 of these nets are passing through C1. So, for the first net it is coming from here, it is going here. For the second net it is coming from here, it is going here. So, with respect to a channel, so a channel is a rectangular region. Okay. So, we assume that pins are on the top or the bottom and the tracks will be laid out like this. So, from this sequence of netlist and the information we have obtained from global routing, we obtain the complete specification for C1 for this particular channel C1, and this is fed to detailed router. So, now detailed router will be having the exact specification for this channel, how many nets are going through it, from where it is coming, from where it is going and so on. Okay. This is the basic idea. The global router will give information like this, from where you can compile information for every channel and the information from every channel will be solved individually and independently by the detailed router. So, it is like a divide and conquer problem. Okay, fine. So, for next lecture we shall be looking at some more global routing algorithms. So, how they work, and then we shall be moving towards detailed routing in the next week. Thank you.